Hi, this is Mrs. Villette, and this video is on section 9.3 exponential functions. Before we launch into what an exponential function is, I want to give you an example that you've seen before when we discussed sequences and series. When we were studying sequences and series, we would often see a list, if we just focus on the y values, something like 7, 10, 13, 16. And we would look at that list and we would try to determine if that was an arithmetic or a geometric sequence. Now notice I've got x values here as well, so x goes 1, 2, 3, 4. We could also see something where our x's go 1, 2, 3, 4, but then our y values go 5, 10, 20, 40. The difference between these being whether or not the function has a constant amount of increase. So in this first example, the y values are always increasing by 3. Or if the function has a constant factor of increase, which means it's multiplying. So in this example, I can see to get to 10, I could either think of it as 5 plus 5, but that pattern doesn't work for the next ones. It looks like it's always being multiplied by 2. And of course, we know how to write equations for these. So this first one is just a linear equation, and the 3 is actually the slope. So it's y equals 3x plus, we need to figure out at 0 what this function would be. While at x equals 1 at 7, it's going up by 3, so in order to go down to 0, I'd need to go down by 3, so it would be 3x plus 4. Now for the second one, I know that there's going to be a 2 to the x somewhere, and there's going to be a value here that represents the starting value. And the starting value for us here will actually be when x equals 0. We can work backwards to see that if x is 1 and y is 5, then when x equals 0, y would have to be half that, or 2.5. So the formula here is y equals 2.5 multiplied by 2 to the x. Our first example was a linear equation, which was similar to what we saw when we studied arithmetic sequences. And our second example is actually a form of an exponential function, which is very similar to a geometric series. Our first objective is to graph exponential functions. We've seen examples before when we were in Unit 7, where we had a base, something like 8, and the exponent was a fraction, like 8 to the 1/3. We of course know that 8 to the 1/3 is the same thing as the cube root of 8, which would be 2. If we look at this expression b to the x, where we have some real number base b, so here the b is a number and the x is the variable. As long as the b is a real number that's greater than 0, then we can actually define b to the x for any value of x, including irrational numbers. So we've seen it for whole numbers. For example, we could see 2 squared, which we know to be 4. That's a base of 2 and an x of 2. We could see 2 to the 1/2, which would be the square root of 2. But we can also do things like 2 to the pi. It's a little bit weird to do that, and usually we'll let our calculator do that, and we'll concentrate on values that we can evaluate by hand. An exponential function. First, we need to define an exponential function. So an exponential function is a function of the form f of x equals b to the power x, where b is greater than 0 and b is not equal to 1, and then x is just any real number. We can graph exponential functions of the form 3 to the x, 5 to the x, half to the x, etc., by substituting in values for x and finding corresponding y values, which will give us ordered pairs. Right now, we haven't graphed these yet, but we will see that all of our exponential functions will be one-to-one functions. They'll have a y-intercept of 0, 1, which I call the anchor point. They will have no x-intercept unless we start transforming them. The domain will be negative infinity to infinity, and the range will be 0 to infinity. It's best to see these properties exhibited by doing an example. We have f of x equals 2 to the x and g of x equals 4 to the x, and we want to graph them on the same set of axes. We will start by making a t-chart. Since there aren't any x values provided, we'll just start by deciding on some of our own x values, maybe 0, 1, 2, 3. We'll substitute those in, so 2 to the power 0 is 1, 2 to the first is 2, 2 squared is 4, 2 cubed is 8. Now we want to have some negative x values as well, so let's try negative 1, negative 2, negative 3. 2 to the power negative 1 means 1 over 2. 2 to the negative 2 means 1 over 2 squared, or 1/4. And then, of course, this would be 1/8. We'll start by just graphing these ordered pairs for 2 to the x. We have the point 0, 1, 1, 2, 2, 4, 3, 8. Then we also have these fractional pairs, negative 1, 1/2. And we start to get to a point where it's really hard to graph these, negative 2, 1/4, and then negative 3, 1/8. If I zoom in really close, I can get pretty accurate, but otherwise, I'm just sort of guessing where these points go. Now, we might be able to add one more ordered pair on here, so if I do 2 to the 4th, I would get 16. So we could put that one on as well. And then we're going to try to connect these with a nice, smooth line. Notice I called it a line, but it actually is more of a curve. So this is my f of x equals 2 to the x. Notice it has the properties listed on the previous slide. It's 1 to 1, passes the horizontal line test. It has that anchor point of 0, 1. It has a domain of negative infinity to infinity and a range of 0 to infinity. In fact, this function has a horizontal asymptote right here at the line y equals 0. Now to do 4 to the x, we don't do anything that's all that different. We're just going to plug in the same ordered pairs. Now with my t-chart, remember we're plugging in the x values. We're now sort of ignoring this middle column. So here I'm doing 4 to the power 0, which is 1, 4 to the first, which is 4, 4 squared, which is 16. Now I can do 4 cubed, but I won't actually be able to graph it. 4 cubed is 64. 4 to the power negative 1 is 1/4. 4 to the negative 2, 1/16. And then our last one is 1/64. And again, that 1/64 is going to be pretty hard to graph. Now we'll transfer these ordered pairs onto a graph. Notice that we still have the point 0, 1. And then we'll also have a different point, 1, 4. And then we're already up here at 2/16. At negative 1, we're at 1/4, which should be below this one. And then 1/16, 1/64. So this one gets closer to the x-axis faster. But then on the other side of the y-axis, it grows more quickly. So it shrinks quickly to the left, but it grows quickly to the right. Notice they're both still 1 to 1, have that same horizontal asymptote and that same anchor point. Example, that the 4 to the x graph grew faster than the 2 to the x graph. Now you might wonder what happens when I make the base small. Notice in our but if we make small values of our base, so fractional values, we can still create a perfectly acceptable graph. It's just going to change what the graph looks like. We'll stick with similar values of x, but maybe we don't need to do as many since we know what the basic shape is. So 0, 1, 2, negative 1, negative 2. 1/2 to the 0 is 1. 1/2 to the first is a half. 1/2 squared is a quarter. When we get into the negative exponents, this is where it gets a little bit trickier. So we have 1/2 to the power negative 1, which of course flips the fraction, making it 2/1 to the first, or 2. and 1/2 to the negative 2 makes it 2 over 1 squared, or 4. So these are very similar values to what we saw before, but they're actually going to result in a decreasing function instead of an increasing function. Now we plot our ordered pairs. 0, 1 is our anchor point. Then we had 1, 1/2, 2, 1/4, negative 1, 2, negative 2, 4. Same shape function, we would also have negative 3, 8. And then we'll connect those with a nice smooth curve. And now we have a decreasing function that still has the same properties, same domain, same range, same anchor point, still 1 to 1. Similar idea goes for 1/4 to the x. I'll fill in the table quickly, and you can take a look and check your work. So there are ordered pairs for 1/4 to the x, same anchor point, but then at 1 we're at 1/4, so we're lower. I can't even really graph 1/16. Negative 1, 4, negative 2, 16. And again, connect them with a smooth curve. So this one looks very similar. These actually are reflections over the y-axis of the previous example. These do have a horizontal asymptote, but no vertical asymptote. So the horizontal asymptote is this line, y equals 0, that these functions are approaching as x goes to infinity. What we've learned from the past examples is that for all exponential functions where the base is greater than 1, we're going to have exponential growth. So for example, 2 to the x, 1.1 to the x, 3 to the x, etc., are all going to look very similar, and they're all passing through this anchor point of 0, 1. The different bases will change the steepness of that graph. Similarly, for exponential functions where the base is between 0 and 1, we're going to get that decrease instead. So examples would be 1/2 to the x, 0.2 to the x, etc. They will all pass through that same anchor point, and the value of the base again changes the steepness of the graph. Now let's look at graphing some of these exponential functions with transformations. The same idea still holds. We are going to plug in values of x. 0, 1, and 2 are good candidates, and then we also want to get some negative values in there as well. We could also base this graph off of the 2 to the x graph we've already made, and notice that this change in the exponent corresponds to an inside change, which would actually mean to shift left 2 units. The table of values will actually take care of that for us, though. When I plug in 0, I would get 2 to the 0 plus 2, or 2 squared, which is 4. 2 to the 1 plus 2, or 2 cubed, which is 8. 2 to the 2 plus 2, 2 to the 4th, which is 16. 2 to the negative 1 plus 2, or 2 to the 1st, which is 2. 2 to the 0 here, which is 1. 2 to the negative 3 plus 2, or 2 to the negative 1, which is 1/2. And then we simply graph these ordered pairs and connect them with that shape we've been exploring in these last examples. Here are ordered pairs, and then we connect them with a smooth-ish increasing curve. And we make sure that we don't cross that horizontal asymptote at y equals 0. Now this function has a couple more transformations on it, negative 3 to the x plus 1. One of the transformations it has on it is a shift up 1, and we'll need to pay attention to that because it will actually change our asymptote. First, we'll make our t-chart. Remember, if the t-chart isn't given to you, that you just need to pick your own x values and do some positives and some negatives. When we plug in 0, we get negative 3 to the 0 plus 1. Now the 3 to the 0 part is 1, but then we have a negative in front of it. So this is actually negative 1 plus 1, or 0. Negative 3 to the 1st plus 1, negative 3 plus 1, or negative 2. Negative 3 squared plus 1. The exponent is only applying to the 3, so this becomes negative 9 plus 1, or negative 8. Now we start putting in negative exponents. So negative 3 to the negative 1 plus 1 is negative 1/3 plus 1, or 2/3. Negative 3 to the negative 2 plus 1 is negative 1/9 plus 1, or 8/9. And then the last one is 26/27. See if you can figure out how I got that value. Go ahead and scale our axes just by 1. We don't want to assume a scale. And then we'll start plotting these points. 0, 0, go through the origin. 1, negative 2, 2, negative 8. Then we have negative 1, 2/3. Zoom in a little bit to approximate where that 2/3 is. Then we have negative 2, 8/9. We're getting pretty close to 1. It's going to be hard to distinguish exactly where we are. And then negative 3, we're at 26/27, which is even closer to 1. Trying to connect these with that same shape that we've been seeing, it looks like this one is upside down though. And that should make sense because that negative out in front of the 3 actually flipped this upside down. One thing you should notice is we kept getting closer to 1, so it appears that y equals 1 is the value of our horizontal asymptote. And in fact, you can see that number right here. It's the number that's added. That corresponded to a shift up 1 unit. If we think about transformations. So that shift up 1 unit changed the horizontal asymptote from being at 0 to being at 1. Now I should let you know that your homework for the graphing is going to be done on paper, not in my math lab. This next section, solving equations, you will do in my math lab. Objective 2 is to solve equations of the form b to the x equals b to the y. This is based on the uniqueness of b to the x. Since b to the x is a one-to-one function, if we say b to the x equals b to the y, we're saying that the outputs are the same. That means these exponents must be the same. So b to the x equals b to the y is equivalent to saying x equals y. It's best to see an example to understand how this uniqueness property works. Let's say we want to solve 6 to the x equals 36. Right now it's not written in the form b to the x equals b to the y, but I can recognize that 36 is actually 6 squared. So 6 to the x equals 6 squared. That must mean that x equals 2. Once we've gotten them to the same base, then we just look at the equation that appears in the numerator. These will rarely be written in that form already. We'll have to do a little bit of work. So example B, 9 to the 2x equals 1. I'm going to look at these bases, 9 and 81, and see if there's a way that I could write them in terms of a common base. Well, I happen to know that 81 is 9 squared. And now that they have the same base, I will just examine the exponent equation. 2x plus 1 equals 2, or 2x equals 1, or x equals a half. This one we should go ahead and check. The previous example, it was pretty clear. I'm plugging in 1/2 in for x and seeing if that equals 81. 2 times a half is 1, so 9 to the 1 plus 1, or 9 squared equals 81. That checks. Now our last example on this page has fractions in it. 1/27 equals 3 to the 2x. First of all, let's just look at the 27 and the 3. Even though the 27 isn't a base, we will work on getting it to be like that. The relationship I can see is that 27 is 3 cubed. Now I don't have this in the form b to the x equals b to the y. What I want to do is take this 3 cubed that's in the denominator and bring it up to the numerator. And in order to do that, I make its exponent the opposite. So 3 to the negative 3 equals 3 to the 2x. Then we do the exponent equation, negative 3 equals 2x. so x is -3/2. This deserves a check, so we'll go and plug back into the original equation. Notice that the 2's cancel, and I get 1/27 equals 3 to the -3, which I know to be true. Let's look at a slightly more complicated example. We have 4 to the 3x subtract 6 equals 32 to the 2x. I can't think of a way to write 42 in terms of powers of 4. But let's look at prime factoring each one of these numbers. 4 we know is 2 squared. 32, maybe you don't know this, but if you break it all the way down, you get 2 to the 5th. It looks like they can both be written in terms of 2's. So we go ahead and we replace 4 with 2 squared. Now this is still to the power 3x subtract 6, and we replace 32 with 2 to the 5th, still to the power 2x. When I have a power raised to a power like this, I multiply the exponents, keeping that base of 2. So 2 to the 6x subtract 12 equals 2 to the 10x. Then I just solve the exponent equation. 6x subtract 12 equals 10x. If I subtract x from both sides, I would get -4x, and I will add 12 to the other side. So x equals -12/4, or -3. Let's go ahead and check this. So 4 to the 3 times -3 subtract 6 equals 32 to the 2 times -3. 4 to the -15 equals 32 to the -6. At this point, unless you rewrite everything in terms of 2's, you can't really tell if these are the same number, but you could go ahead and evaluate on your calculator and see if it checks, and it does. One thing I realized I've been forgetting to do is put our answer in a solution set. So go back in your notes and fix those other ones. And for this one, we would write our solution set containing just the number -3. Now let's look at some problems that are modeled by exponential equations. There are lots of applications that use exponential equations. For example, in the next section, we'll talk about exponential growth and decay, which you may have seen in chemistry. Also, compound interest formula, we've seen this before. This uses exponential functions as well. We'll start with a growth and decay problem. So Texas law states that the assessed value of a home may increase by at most 10% per year. If a house was valued at $300,000 in the year 2000, and the assessed value increased by the maximum amount, so 10%, then A of x equals 300,000 multiplied by 1 plus 0.10 to the power x gives the assessed value after x years. Notice here that we're taking 1, which is 100%, and adding 10% to that, then raising it to the number of years past. What is the assessed value of the house this year? Well, it was worth $300,000 in the year 2000, so that's going to be my year 0. This year is 2018, which means we're going to plug in 18 for the x. So we're saying A of 18, or the amount, the assessed value of the house after 18 years, is 300,000 multiplied by, we could simplify this to 1.10 to the power 18. And we simply enter this into our calculator by entering 300,000 parentheses 1.10 caret 18. You can see that I've entered this just into Desmos and got a pretty astonishing value, $1,667,975.19. So 10% growth after 18 years gives you quite a hefty increase in the value of real estate. In fact, if you can find 10% interest anywhere that somebody will pay you, you should put all of your money in that. Okay, an example with compound interest, same idea. We're going to use our A equals P times 1 plus R over N to the NT, where P is the principal, A is the amount in the account, R is the annual interest rate, N is the number of compounding periods per year, and then T is the number of years. In this problem, we need to find out the amount if we take $5,000 invested at 6% compounded monthly for 18 years. So P is 5,000. The rate is 6%. We're compounding monthly, so the N is 12. We're raising it to the 12 times 18. Again, we're going to use a calculator for this. And it might help if you do the 12 times 18 first, just to make sure that you enter it appropriately. If you're entering this in a TI 83 or 84, you want to make sure that when you do your caret, this is what it would look like, caret parentheses 12 times 18. I'm going to use Desmos just because that's what I have on my iPad to evaluate. And you can see up here the value I got from Desmos, rounded to the nearest cent, $14,683.83. So compound interest is pretty amazing. If you could get 6% annual interest, compounding monthly makes it even better. You would end up almost tripling your investment in 18 years. Now, if you don't do it monthly, you only get that 6% once per year. You don't get quite as much. You can see off to the side at the bottom here, if you just compound once per year, so annually the N would equal 1, you only end up with $14,271.70. So a little bit less, but that 6% interest over 18 years still does give you quite a bit of growth.